In this lecture, we will learn the basic syntax of TensorFlow. Today, we will learn what TensorFlow is and how to install TensorFlow. Lastly, we will study the basic syntax of TensorFlow 1. TensorFlow is an open-source machine learning library released in 2015 based on a project called DisBelief developed by Google. Since then, it has been continuously updated by open source developers and Google. TensorFlow supports classes and functions used to implement various machine learning related models. It also provides GPU acceleration using functions of the CUDA library. Now, let's install TensorFlow. In fact, in the next few lectures, we won't heavily utilize the computational power of the GPU unit. However, in the second half of the course, we plan to utilize the GPU's computational power more, so I'll explain how to install TensorFlow and CUDA based on a computer equipped with an NVIDIA GPU device. As mentioned in the previous lecture, using Conda, you can easily install CUDA and TensorFlow. If you want to install TensorFlow on your computer using Conda, just enter the command conda install TensorFlow GPU into the terminal. This command installs both CUDA and TensorFlow on your computer. To check whether TensorFlow CUDA Toolkit and CUDA Deep Neural Network library are installed properly, run the following Python program. If CUDA and TensorFlow are successfully installed through Conda, the log shown on the slide will be displayed, and true will be printed. You can also utilize a command called NVIDIA SMI to verify that the GPU device is working when training a deep learning model or performing inference using the GPU device. If you install the NVIDIA graphics driver in Ubuntu, this program is also installed. If you type NVIDIA SMI in the terminal, the GPU state at the moment is printed to the console. This allows the user to check the GPU resource usage status at the moment NVIDIA SMI runs. The user can check if the deep learning model is loaded on the GPU device through the usage of VRAM. A bug sometimes occurs when loading deep learning models onto GPU device. This can happen when VRAM out of memory error occurs due to the deep learning models being too large. Also, if the computer does not have enough power supply, the computer shuts down. Other problems are usually caused by bugs in the code or hardware problems. In the previous slide, I mentioned cuDNN in addition to the CUDA toolkit. cuDNN is a neural network library implemented based on the CUDA library. We will learn about the term neural network in the next lecture. For now, you can think of cuDNN as a library that provides functions used to implement deep learning models. TensorFlow utilizes cuDNN functions to train and infer models using NVIDIA GPU devices. Therefore, this library must also be installed along with CUDA Toolkit. TensorFlow currently has two versions. Version 1 is a version developed in the past. However, many deep learning model libraries are still implemented in TensorFlow 1. It is good to learn TensorFlow version 1, but you don't need to learn it in detail. Therefore, today we will learn only the basic syntax of TensorFlow 1. Perhaps the version of TensorFlow you installed using Conda is version 2. So in order to study TensorFlow version 1, let's first build an environment to utilize TensorFlow version 1. How can we install multiple versions of TensorFlow on one machine? We can use something called Conda environment. In the previous lecture, I said that Conda is a package installation management software. Also, the Conda software has the ability to manage virtual environments. The virtual environment refers to a system structure that can install and operate the Python interpreter, libraries, and packages in an independent space. These virtual environments are often created and managed by environment management software. Conda also provides the ability to create and manage these virtual environments. If you activate the created virtual environment, you can install and utilize the Python interpreter and packages you want in that environment. And if you deactivate the environment, you cannot access the environment and packages in it. You can create multiple virtual environments, each operating independently. So if you create 2 virtual environments, you can install 2 Python interpreters, and you can install Python packages independently in each environment. In addition to Conda, there are environment management softwares that can be utilized to build virtual environments. However, in this course, it is recommended to use Conda for the convenience of installing CUDA and cuDNN. Conda virtual environments can be activated after creating each virtual environment with a unique name. To use the Conda virtual environment, you must first create a virtual environment, and the name of each virtual environment must be unique. For example, if you want to create a virtual environment named HelloName, you can do so by entering the command on the slide in the terminal. A more detailed explanation of how to use Conda virtual environment can be found in the slides and links on the course page. After creating the virtual environment, you can activate the virtual environment with the command conda activate. If you created a virtual environment called HelloName before, you can activate the HelloName virtual environment by typing conda activate HelloName in the terminal. The HelloName virtual environment has a separate Python interpreter, and packages installed in this virtual environment cannot be accessed from other environments and do not affect other environments. After activating the virtual environment, you can install any package you want in it. For example, if you want to install TensorFlow version 1.14.0, enter the command on the slide after activating the environment. If you want to use a different version of the TensorFlow or Python interpreter, you must first deactivate the active environment. If you want to deactivate an environment, you can enter the command conda deactivate in the console in the enabled environment. To remove the created virtual environment, simply enter the command shown in the slide. For example, if you want to remove a virtual environment named myenv, you can remove the virtual environment by entering the first command on the slide. Similarly, if you want to remove the HelloName virtual environment you created earlier, you can enter the second command on the slide. After conda is installed, the base you see on the left side of the terminal means that conda's default virtual environment base is enabled. All virtual environments are created in the base, and if any package is installed in the base, the package installed in the base may be copied when a new environment is created. Since we will be dealing with 2 versions of TensorFlow in the future, we will first delete the TensorFlow installed in the base. Delete TensorFlow GPU by entering the command shown in the slide, and we will create a new environment T1. Please do not delete this environment until the end of this course. If you created the T1 environment, activate it, and install version 1.14.0 of TensorFlow GPU in the T1 environment. Now, with that environment active, create a code file called t1.py, write the following code, save it, and run it in the T1 environment. Let me start explaining the code. In TensorFlow, any data or model is processed as a type called tensor. For example, the 2 lines of code shown in the slide create 2 tensor variables. If we print the types of 2 variables, you can see that their data type is tensor as shown in the slide. Let's look at the next line. A variable called result is assigned the return value of a function called TensorFlow.multiply. By looking at this code, you probably assume that the result of multiplying 2 arrays is stored in a variable called result. However, when we print the result variable, we can see that the red text on the slide is printed on the console. You may think something is strange. First, let's print the type of the result variable. Strangely, the result variable does not store the calculation result, and the type of the result variable is tensor. TensorFlow treats both data and data expressions as a data type called tensor. In TensorFlow, operations are performed only when a session is executed. If you think of the return value of the TensorFlow.multiply function as a computational model rather than a computational result, it'll help you understand. This model does not perform any operation and must be executed within a session to return the result of the operation. Now, let's run the TensorFlow model with a session and check the calculation results. In TensorFlow 1, the session class instance is initialized as follows. The model is passed to the method run of the session class, and the model is operated and the result is returned. In this code, the result of the operation is stored in the output variable. And if we check the type of the output variable, we can see that the operation result in the TensorFlow session is returned as an ND array type. Let's run a bit different code this time. Write the code shown in the slide in a new file, save it, and run it. In the code you just saw, you can think of TensorFlow.placeholder as a variable of type tensor. If you decide what type of data to enter in the placeholder, you can store the data in this variable later and use it as tensor type data. In this code, it is defined that data of type TensorFlow.float32 comes in the placeholder. Please note that the data type used in TensorFlow is different from the primitive data type of Python. Adder equals a plus b in line 7 is to assign a model that adds tensor A and tensor B to a variable called adder. Unlike the code we saw earlier in T1.py, this code uses the plus operator. Since the data type of tensor is treated as a class in Python, it is possible to utilize the plus operator with operator overloading. However, not all Python operators can be used for tensor operation, so use the TensorFlow operation function instead of the operator when implementing the TensorFlow operation model. Once the model has been built, you can use session to get the model's calculation results. A placeholder can get data using a technique called feeding. Feeding refers to passing dictionary data to a parameter of the session run method. For example, if you want to assign 3 and 4 to 2 placeholders A and B, define the dictionary as in the code in line 10 and pass it as an argument to the feedDict parameter. When you want to perform an operation between lists of multiple data, you can pair the list with each placeholder as in line 11 and pass it to feeddict. If you run the program, you can see that the operation was performed as expected. By using feeddict like this, we can get data from standard input or externally and perform the model operation. This time, try implementing the following program yourself. Write a TensorFlow 1 program that takes 3 numbers as input from the user and prints the value multiplied by 0.4. Pause the lecture video, implement the program, and then resume the lecture. For example, we can implement a program like this. Although the string type data list was assigned to the P1 placeholder, the program works correctly because the type is defined as TensorFlow.float32 in the placeholder. Congratulations! Now you have a basic understanding of how TensorFlow 1 works. You can also learn more about TensorFlow 1's features and syntax, but you don't need to know more than this for this course. Even if you do not know TensorFlow, you can still learn AI programming in the future. And future lectures will be conducted with frameworks other than TensorFlow. Some of you may be wondering about TensorFlow 2 instead of TensorFlow 1. However, the syntax of TensorFlow 2 is different from that of TensorFlow 1, and it is almost identical to the deep learning library called Keras. Therefore, the syntax of TensorFlow 2 will be covered in future lectures on Keras. Let's dig into the differences between TensorFlow 1 and TensorFlow 2 a little more. First, TensorFlow 1 is more difficult to learn and handle than TensorFlow 2. This is because TensorFlow 2 has been redesigned with a reference to a library called Keras. Also, TensorFlow 1 and 2 are not very compatible. And although TensorFlow 2 was built with reference to Keras, it is not quite the same as Keras. This is because the source code of Keras was partially taken and redesigned. Although the usage of TensorFlow 2 itself is almost identical to that of Keras, there are some differences from Keras. While developing, if you want to know the version of the TensorFlow you're currently using, you can open a Python shell and enter the following code. Converting TensorFlow 1 code to TensorFlow 2 code is officially supported. You can find information on how to convert the TensorFlow version in the following link. However, this method is not very helpful for converting TensorFlow 1 open source code written by others. Therefore, when using an open source TensorFlow model developed by others, do not change the TensorFlow code version of the model. And we recommend that you use the TensorFlow version that was used to implement the model after creating an independent virtual environment for the model. If you do not want to use the Conda virtual environment, you can use virtual environment softwares called virtualenv or Docker. However, since this course is based on Conda, instructions on how to use this software will not be provided. When you run the TensorFlow code, the log is often very long. You can change the log printing policy by using the following code. If the log level is set to 1, the info type log is not printed. If the log level is set to 0, all logs are printed. If the log level is set to 2, info and warning logs are not printed. If the log level is set to 3, all logs are not printed. In general, when doing AI programming, it is often necessary to check the warning and error logs, so we recommend setting the log level to 1. In the next lecture, we will learn the basics of deep learning. Thank you.